start at the very beginning. What exactly is a polymer? The word itself comes from Greek, poly meaning many, and meros meaning parts. At their core, polymers are giant molecules or macromolecules built by linking together thousands of tiny repeating units. These units, called monomers, are the essential building blocks. Imagine a long chain made by snapping together identical beads. Each bead is a monomer, and the whole chain is a polymer. This simple concept is the foundation for a vast world of materials, from the DNA in your cells to the plastic in your water bottle. In this video, we'll explore how these fascinating molecules are made, classified, and used in everyday life and advanced technology. To truly grasp polymers, we need to understand monomers. A monomer is a small, single molecule, often bifunctional, meaning it can connect at 2 points. When these monomers undergo a chemical process called polymerization, they link together to form long chains. The number of monomer units in a chain is known as the degree of polymerization. For example, when many ethylene molecules, CH2 equals CH2, are joined, they form polyethylene, the material used in plastic bags and soda bottles. This transformation from simple molecules to complex chains is what gives polymers their unique properties and versatility. Polymerization is the process that transforms monomers into polymers. Think of it as an assembly line where each monomer snaps into place, extending the chain. There are two main types, addition and condensation polymerization. In addition polymerization, monomers add to each other without losing any atoms, while in condensation, a small molecule like water is released as a byproduct. This process is fundamental to creating the wide variety of polymers we encounter daily, from flexible plastics to tough fibers. Let's look at a familiar example, polyethylene. By linking together many ethylene molecules, we get polyethylene, which is used in countless everyday products. Its versatility comes from the way the chains are arranged and how long they are. This simple transformation highlights the power of polymer chemistry in creating materials with specific properties for different uses. Polymers are everywhere, and their diversity is astounding. To make sense of this variety, scientists classify them in several ways. The first is by their source, natural, semisynthetic, or synthetic. Natural polymers are found in plants and animals. Think cellulose, starch, and proteins. Semisynthetic polymers are natural ones that have been chemically modified to enhance their properties, like cellulose nitrate. Synthetic polymers, on the other hand, are entirely man-made, often from petroleum-based chemicals, such as nylon and polyethylene. Natural polymers are the original building blocks of life. Found in both plants and animals, they include cellulose, starch, proteins, and natural rubber. These materials have been used by humans for centuries, long before the advent of modern chemistry. Their structures are often complex, but their origins are entirely from nature, making them essential to biological processes and everyday life. Synthetic polymers bridge the gap between natural and synthetic materials. They start as natural polymers, but are chemically modified in the lab to improve their properties. For example, cellulose nitrate is used in explosives and film, while vulcanized rubber is tougher and more durable than its natural counterpart. These modifications allow us to tailor materials for specific applications, combining the best of both worlds. Synthetic polymers are entirely man-made, often starting from petroleum-based chemicals. These include household names like nylon, toluene, and polyethylene. Their creation in the lab allows for precise control over their properties, making them suitable for a wide range of uses, from clothing fibers to packaging materials. The ability to design polymers from scratch has revolutionized modern life. Another way to classify polymers is by their structure, how the monomer bricks are arranged. Linear polymers have long, straight chains that pack closely together, resulting in high density and melting points. Branch-chain polymers have arms or branches, making them more flexible and less dense. Cross-linked or network polymers are joined by strong covalent bonds, forming a rigid three-dimensional network. Each structure leads to different physical properties and uses. Linear polymers are made up of long, straight chains of monomers. Because these chains can pack closely together, materials made from linear polymers tend to be dense and have high melting points. High-density polyethylene, HDPE, is a classic example, used in products that require strength and durability. The arrangement of the chains is key to the material's properties. Branch-chain polymers have side chains or arms sticking out from the main chain. This prevents them from packing tightly, making them more flexible and less dense. Low-density polyethylene, LDPE, is a good example. Cross-linked or network polymers, on the other hand, have chains joined by strong covalent bonds, forming a rigid three-dimensional network. Bakelite is a classic example, known for its hardness and heat resistance. Polymers can also be classified by how their monomers are joined. Addition, chain growth, polymerization involves the repeated addition of monomers, usually with double or triple bonds, without losing any atoms. Condensation, step growth, polymerization, on the other hand, involves a reaction between two different functional groups, releasing a small molecule like water as a byproduct. Each mode leads to different types of polymers with unique properties. In addition, polymerization, monomers with double bonds, like ethylene, join together to form long chains without losing any atoms. This process is straightforward and efficient, making it ideal for producing large quantities of materials like polyethylene. The resulting polymers are often used in packaging, containers, and countless other products. Condensation polymerization involves two different monomers, each with functional groups that react to form a bond, releasing a small molecule like water. Nylon 66 and Dacron are classic examples. This process allows for the creation of complex polymers with tailored properties, used in textiles, engineering, and more. The behavior of polymers is also determined by the molecular forces between their chains. These forces, such as van der Waals, dipole-dipole interactions, and hydrogen bonding, affect whether a polymer will snap, stretch, or melt. Based on these forces, polymers are classified as elastomers, fibers, thermoplastics, or thermosetting polymers, each with distinct properties and uses. Elastomers are polymers with the weakest intermolecular forces. Their chains are randomly coiled and held together by just a few crosslinks. When you pull on an elastomer, the chains straighten out, allowing the material to stretch significantly. When released, the crosslinks pull the chains back to their original state, giving elastomers their high elasticity. Natural rubber, bounasse, and neoprene are common examples. Fibers are polymers with the strongest intermolecular forces, often hydrogen bonds or strong dipole-dipole interactions. Their chains are long, thin, and symmetrical, allowing them to pack closely together. This gives fibers high tensile strength and a high modulus. They don't break easily under tension and don't stretch much. Examples include nylon 66, turreline, and silk. The structure of fibers allows them to pack closely, resulting in high crystallinity. This makes them ideal for applications where strength and durability are essential, such as textiles and industrial materials. Nylon 66 and turreline are widely used in clothing, ropes, and even parachutes, while silk remains a natural marvel for its strength and luster. Thermoplastics have intermolecular forces that are intermediate, stronger than elastomers but weaker than fibers. When heated, the secondary bonds are overcome, allowing the chains to slide past each other and the plastic to become a thick liquid. When cooled, the bonds reform, making the process reversible and the material recyclable. Common examples include polyethylene, polyvinyl chloride PVC, and polystyrene. Thermosetting polymers start as low molecular weight semifluids. Once heated, they undergo extensive cross-linking to form a giant 3D network of covalent bonds. This creates a rigid, permanent structure that doesn't melt when reheated. Instead, it burns or chars. These polymers are hard, brittle, and heat-resistant, making them ideal for electrical switches and unbreakable plates. Bakelite and melamine are classic examples. Thermosetting polymers are used in applications where durability and heat resistance are crucial. Electrical switches, handles of utensils, and old telephone casings often use bakelite due to its excellent insulating properties. Melamine is used for unbreakable plates and kitchenware, thanks to its toughness and resistance to heat. These materials are essential in both household and industrial settings. Polymers can also be classified based on the nature of their monomers. Homopolymers are made from a single type of monomer, while copolymers are formed from two or more different monomers. This distinction allows for a vast range of material properties, as combining different monomers can yield polymers with unique characteristics tailored for specific applications. Homopolymers consist of repeating units of a single monomer, resulting in uniform properties throughout the material. Copolymers, on the other hand, are made by combining two or more different monomers. This allows for the creation of materials with a blend of properties, such as increased flexibility, strength, or chemical resistance, depending on the chosen monomers. Polymerization is the chemical process of linking small monomer units into a giant macromolecular chain. Think of it as the assembly line of chemistry, where each monomer is added one by one to build a long, functional chain. The two primary ways these molecules connect are addition and condensation polymerization, each leading to different types of polymers with unique properties. In addition polymerization, monomers add together without losing any atoms, forming long chains quickly and efficiently. In condensation polymerization, two different monomers react, releasing a small molecule like water as a byproduct. Both processes are essential in creating the diverse range of polymers we use every day, from plastics to fibers and beyond. Natural rubber is a classic example of a polymer formed by addition polymerization. Its monomer is isoprene, and the resulting polymer is called cis-1, 4-polyisoprene. The chains are held together by weak van der Waals forces and have a coiled structure, giving rubber its elasticity. Applications include erasers, elastic bands, and shoe soles for non-heavy-duty uses. Vulcanization is a process that transforms natural rubber into a tougher, more durable material. By heating rubber with sulfur and additives, cross-links are formed at the reactive sites of double bonds, creating a 3D network. This prevents the chains from sliding, making the rubber suitable for car tires, conveyor belts, and heavy-duty industrial hoses. Vulcanization process gives rubber the toughness needed for demanding applications. Car tires, conveyor belts, and industrial hoses all rely on vulcanized rubber for their strength and resilience. This innovation has had a profound impact on transportation and industry, making rubber a vital material in modern life. Neoprene is a synthetic rubber made from the monomer chloroprene through free radical addition polymerization. It offers superior resistance to oils, vegetable fats, and solvents, making it ideal for gaskets, hoses, and wetsuits. The ability to engineer such materials has expanded the range of applications for synthetic polymers. Teflon, or PTFE, is made from tetrafluoroethene monomers via addition polymerization. It is chemically inert and highly resistant to heat, making it perfect for nonstick cookware coatings, oil seals, and gaskets. Its unique properties stem from the strong bonds between carbon and fluorine atoms in its structure. Bakelite is a phenol formaldehyde resin formed by condensation polymerization. Initially, it forms a linear polymer called novolac, but upon heating with more formaldehyde, it undergoes extensive cross-linking to become a hard, infusible solid. Bakelite's high heat resistance and electrical insulation made it a popular choice for electrical switches, utensil handles, and old telephone casings. Nylon 66 is made from adipic acid and hexamethylnediamine through condensation polymerization. The reaction eliminates water and forms a polyamide chain. Nylon 66 is prized for its high tensile strength, making it ideal for textile fibers, brush bristles, and climbing ropes. Its durability and versatility have made it a staple in both industrial and consumer products. Urea formaldehyde resin is formed from urea and formaldehyde via condensation polymerization. The result is a highly cross-linked thermosetting network, making it extremely tough and durable. It's widely used for making unbreakable cups, laminated sheets, and adhesives for plywood, thanks to its strength and resistance to moisture. Polyethylene terephthalate, or PET, is made from ethylene glycol and terephthalic acid through condensation polymerization. It forms an ester linkage with the loss of water. PET is commonly known as Turylene or Dacron and is used in plastic bottles, food containers, and magnetic recording tapes. Its strength, clarity, and chemical resistance make it a popular choice for packaging. Kevlar is an aromatic polyamide made from 1,4-phenylenediamine and terephthalochloride via condensation polymerization. Its chains are held together by strong hydrogen bonds, giving it a strength-to-weight ratio 5 times greater than steel. Kevlar is used in bulletproof vests, aerospace components, and high-performance tires, making it a material of choice for demanding applications. Biodegradable polymers are designed to break down into harmless products like water, carbon dioxide, and biomass through the action of microorganisms or enzymes. These eco-friendly materials are increasingly important as we seek sustainable solutions to plastic pollution. Their ability to degrade naturally makes them ideal for applications like packaging, agricultural films, and medical devices. Secret to biodegradable polymers lies in the presence of polar functional groups like esters or amides in their main chain. Water molecules can attack these bonds through hydrolysis, breaking the long chain into smaller, water-soluble pieces. Microorganisms also produce enzymes that target these linkages, effectively eating the polymer and converting it into harmless substances. Biodegradable polymers are used in a variety of applications where environmental impact is a concern. From compostable packaging and agricultural films to medical implants that dissolve in the body, these materials offer sustainable alternatives to traditional plastics. Their ability to break down naturally helps reduce waste and pollution. Fullerenes are a unique class of carbon allotropes characterized by hollow, closed-cage structures made of fused hexagons and pentagons. The most famous is C60, also known as Buckminster fullerene or buckyball, which resembles a soccer ball. Discovered in 1985, fullerenes are known for their high electron accepting ability and have opened new frontiers in materials science. C60 fullerene consists of 20 hexagons and 12 pentagons, with every carbon atom sp2 hybridized and bonded to 3 others. Its spherical shape gives it unique properties, such as solubility in organic solvents and the ability to become incredibly hard under high pressure. C60 solutions are known for their striking magenta or purple color. Fullerenes have a wide range of applications. They can act as superconductors when doped with alkali metals, serve as catalysts due to their high surface area, and function as lubricants thanks to their spherical shape. In cosmetics, they are used in high-end anti-aging creams for their ability to neutralize free radicals. Their versatility makes them valuable in both industry and research. Fullerenes are a hot topic in nanomedicine due to their unique cage structure and electronic properties. They act as powerful antioxidants, soaking up free radicals that cause cell damage and aging. Fullerenes can also be used for targeted drug delivery, as their small size allows them to penetrate cell membranes. Research even suggests they may inhibit HIV protease, opening new possibilities in antiviral therapy. Fullerenes are not found in large quantities in nature. Instead, they're synthesized in the lab using the electric arc discharge method. An electric arc is struck between two graphite electrodes in an inert atmosphere, vaporizing the carbon, which then condenses into a sooty residue. This soot contains C60, C70, and traces of larger fullerenes, which are then purified using organic solvents and chromatography. Carbon nanotubes, or CNTs, are cylindrical nanostructures made from rolled-up graphene sheets. They are renowned for their exceptional tensile strength, high electrical and thermal conductivity, and low density. CNTs are classified as single-walled or multi-walled and are vital in nanotechnology, electronics, and composite reinforcement. Their unique properties make them promising for a range of advanced applications. CNTs are primarily produced through chemical vapor deposition, electric arc discharge, or laser ablation. They are hollow, cylindrical allotropes of carbon with nanometer-scale diameters and micrometer-scale lengths. CNTs are among the strongest and stiffest materials known, with exceptional thermal and electrical conductivity. They can be metallic or semiconducting, depending on their structure, and are used to reinforce materials and enable new technologies. Unique properties of carbon nanotubes have led to a wide range of applications. They are used in structural composites to make materials lighter and stronger, such as in tennis rackets, bicycle frames, and aircraft wings. In nano-electronics, CNTs are candidates for next-generation computer chips. They also enhance energy storage in batteries, enable advanced water filtration, and serve as drug delivery vehicles in biomedicine.